I want to say many thanks to the organization for giving me the opportunity to do my presentation in remote. These are the outline of my presentation. I will try with this short speech to reply to some easy question, but with not so easy replies that are why we need to have energy storage system in transmission distribution grids, where and how this storage can be placed inside the transmission and distribution grids, which are the more suitable technologies that we can use. And in the second part, I will leave the floor to Lorenzo, that is a researcher with me, that will show to you an Italian case of an energy storage technology that can be considered a possible and application-oriented solution for the integration inside the transmission and distribution grid. So the first question is why today we need to have energy storage in transmission and distribution grids. As you know, energy sector today is playing a fundamental role in facing the problems linked to the environment. In fact, in this moment, many energy policies are being proposed, and among them we have the main objective of decarbonization of the energy sector. And for doing that, there is the need to replace the traditional conventional power plant with renewable energy sources that, as you know, are mainly non-programmable. And thanks to the strong development of non-programmable RES, it is possible to reduce the environmental impact of the electricity generation sector. But at the same time, this revolution requires a deep change in the feature of the production system. In fact, starting from large-scale mainly thermoelectric power plants concentrated in specific points of the power system, we are moving on to a production system that is made of many smaller power plants distributed on the territory and characterized by a random generation profile. Due to that, some new critical issues were born inside the power system. Here I have listed just as example some of them. First of all, the reduction of the adequacy margin on the grid. What does it mean? It means that we don't have sufficient resource in the long term that can guarantee in real-time operation the supplying of the final loads. And this is a big problem in the operation of a real power system. Another example can be the reduction of the power system inertia, whose main consequence is a consequence related to the stability of the transmission and on the dynamic performances of the power system during their operation. And another important issue can be the lack of power plants able to offer frequency and voltage control service that, as you know, are fundamental for the security of the operation of a power system. These are just 3 examples of the critical issues that are present today in the power system with many renewable sources. And which could be a reply? A reply can be the installation, the integration of the energy storages. In fact, through the energy storage, it is possible to give some solution in the midterm to all the problems that we have listed before. And in function of the type of technology that we consider, with different technical and economical feature, we can have a different contribution in the resolution of the problems listed before. So where and how we need to have energy storage inside the transmission and the distribution grid? In general, we can say that the integration of energy storage technologies inside the grids is a measure that increases the flexibility of the power system. The storages can do the system, the power system, more flexible, more able to give a faster reply to the not programmable behavior of the renewable energies. At the same time, we have to consider that through the installation of storage, it is possible to give a fast answer to the issues listed before, because the implementation time of a storage system inside a grid is in generally faster than the implementation of any other measure dealing with the asset, the electrical infrastructure. So is a faster reply in terms of implementation time for supporting the flexibility of the power system. But where it is possible to introduce a storage system inside the grids? The reply is everywhere, because in function of the point where you will put your storage, you can face and try to support the resolution of a given problem in a different way. This is a very simple picture just for showing you what I'm saying graphically. You can solve different problems related to the grid operation using energy storage located in different points. Just for giving you an example, we have here, let me change. Okay, you have here an energy storage system coupled on the high voltage bus bar to a conventional power plant. A type of function of service that this storage system can perform in respect to the whole power system can be a function of load leveling for the generator. But another example can be an energy storage system located inside the high voltage system. And in this case, the ESS can perform a service of frequency control. But you can add also an energy storage system in couple with a wind farm of a solar power plant for performing services in the direction of a better integration of the same renewable energy power plant. You can place energy storage system inside a high voltage, medium voltage electrical substation on both the sides, and you can do different service like voltage control or load leveling of a medium voltage line. You can couple an energy storage system with an industrial power plant, a big load connected to the medium voltage ring of a power system for doing a peak shaving function. So in general, it is possible to integrate energy storage everywhere in any point of a power system for reaching different objectives in favor of a good operation of the power system at all. But which are the services that energy storage system can do in general for a transmission and distribution grid? The same energy storage system can have different utilities from a different point of view. Today, I want to show you a short list of the services that are useful for who is in charge to manage the transmission system and the distribution system that, as you know, are called TSO and DSO. A good summary of the type of services that can be provided to these two operators of the electrical sector is reported inside the Electricity Storage Handbook edited by the Department of Energy of the United States. Here you have the link where you can download this document that of course is public, but here I have tried to summarize all these services. First of all, we have the bulk energy services, the services that are useful both for the production segment and for the transmission segment. And they are mainly two: the electrical energy time shifting used as market instrument, and the electrical energy supply capacity that can be used for reducing the value of the so-called not supplied energies. These two services are in advantage of the whole bulk system. If we focus on the transmission segment, we can find the so-called ancillary services. And as you know, the main ancillary services are those one related to the frequency control, to the voltage control, and to the black start for repowering a system after a blackout. All these services can be provided by storage system integrated inside transmission and distribution grid. Then we have the services useful for the infrastructure, for the transmission and distribution asset. And they can be considered mainly two. The first is the transmission upgrade deferral. It means a deferral of the investment in the transport infrastructure for electricity that is possible if you have a storage system implemented inside the transmission distribution lines. And the second one, that is strongly related to the previous one, is the transmission congestion resolution. When you have a congestion on a given line, if you have a storage system, you can solve the problem of the congestion without acting on the same line. But which storage technologies can give a reply to the problems that we have seen, providing the services that we have listed? Also, in this case, the reply is all the technologies, because as you know, today we have many different energy storage technology available on the market with a different level of maturity. And in function of that, they are able to perform different service to the transmission distribution grid. Among them, we have many electrochemical storage technologies. It means batteries, like lead batteries, lithium batteries, high temperature batteries, flow batteries. We have mechanical storage technologies like pumping, compressed air system, and flywheels. We have pure electric storage technologies like SMAS and supercaps. We have also chemical storage technologies considered in the configuration power to gas. We have thermal storage technologies considered in the configuration power to heat. Each type of technologies has different technical characteristics in addition to the different level of maturity of the same technology. But which are the main feature that we have to consider for understanding why and how each technology can support the planning operation of the transmission distribution grid? The two main parameters, technical parameters that we have to consider are the power and the energy density. This is the well-known Ragone plot that gives you an idea on how each storage technology can give energy or power-intensive service to the power system where it is located. And as you see, different technologies are located in different points of this graph. Here we have the pumped hydropower plant that are the biggest inside and also able to give the maximum value of the energy that can be installed and the maximum time of operation during the charge and discharge phase. On the opposite, we have, of course, the supercapacitor. In the middle, you can find all the different technologies that we have listed before. So if you cross the information on the level of the maturity of the technology with the information on the amount of energy and power that each technology is able to provide, you can say which technology can be used for providing a specific service to the power system. So this is a matrix where this type of crossing is made. Through this matrix, it is possible to see how, in function of the type of application, the type of service, which is the technology able to provide this service. And as you see, each technology can be able to provide some services and not other. It depends on which type of technology that we are considering. So my conclusion is that on the question which energy storage technologies can be useful for the transmission distribution grid, the reply is all the technologies. We need to have mechanical storage, we need to have batteries, we need to have chemical storage, but we need to have also thermal storage, because each technology can give a different answer, a different reply to the specific problem that are in progress inside the power system full of renewable energies. Among these technologies today available, now Lorenzo will present to you an Italian storage technology that can be used, a good solution, application-oriented as a hybrid system. So let me leave the floor to Lorenzo, that I think is here with you. I don't know if...
Can you hear me?
Yeah, perfectly, Lorenzo. Thank you.
Thank you, Maria Carmen. I present myself. I am Lorenzo Romagnoli, and I am the researcher at University of La Sapienza of Rome, and in collaboration with the Professoressa Maria Carmen Falvo. And I'm pleased to be here to present an Italian thermal energy storage technology that is developed by Magaldi, in which I work as application engineer and process engineer. And the change of slide, okay. Then
I'm not sharing my screen so that you can share.
Okay. I done by myself. Okay. Starting from the name MGTES. MGTES stands for Magaldi Green Thermal Energy Storage. MGTES is a part of sensible heat thermal storage. In fact, uses simple silica sand to store the energy in form of heat of high temperature. And as you can see in the bottom of the picture, the MGTES is represented as a simple receiver, a simple container that include silica sand that are immersed active elements for the charging and discharging phase. In particular, with the number 3, you can find electrical resistors that are immersed directly in the sand to charge the system. And with number 4, represented the immersed heat exchanger for the discharge of power. The receiver is thermally insulated to reduce at minimum the thermal losses through the external. But the main feature of this technology is the fluidization. In fact, the sand bed is fluidized through the injection of a quantity of air from the bottom of the sand, and the mix of the air and solid particles that behaves like a fluid increase the performance in terms of increasing the heat exchange coefficient, in particular for the charging and discharging phase, but also increasing the temperature distribution inside the sand bed during the storage phase. As you can see on the right side of the picture, we have the air line for the fluidization, in which is contained a preheater of the air that is injected to the sand bed in a pressurized way, just to win the hydrostatic of the sand bed. And on the right side, the steam line that is useful to produce steam at temperature required by the process. Mainly, MGTES as a simple energy storage system work with 3 main phases. The charging phase, that is mainly consists in the drawing of the electricity from the grid or directly whatever power sources are available from the grid. And the electrical resistor uses this electricity to heat up the sand that are in direct contact. With simple Joule effect, we can heat up the sand with the maximum temperature reachable. The second phase is the storage phase, where the sand maintains its temperature for a longer period of time. And the third phase is the discharging phase, where the immersed heat exchanger draws the thermal energy from the stored in the sand to provide and produce steam or whatever fluid, thermal fluid for the process. The application, mainly the main application is power to heat, and the maximum temperature of the sand that can be reached by the sand is over the 1000 degree. But due to the material that are used to produce the immersed elements like electrical resistors and also immersed heat exchanger, the maximum temperature reachable by the sand is set to 620 degrees. And also, the thermal fluid produced can be produced in a range between 200 and 500 degrees that can be used in a large quantity of the industrial sector, in particular pulp and paper, food and beverage, and others. The round trip efficiency in this configuration, then in power to heat configuration, is around 90%. This because around 5% point percentage is due to the fluidization system that is activated only during charging and discharging phase, and disactivated when the system have to store the heat for a longer period to reduce the thermal losses. In fact, the thermal losses are estimated less than 2% per day as a self-discharging rate. Okay, thanks to this feature, MGTES can be defined as a long-term energy storage system because can offer size of duration of different discharging time between 4 and 150 hours. In particular, the actual development stage of MGTES correspond to a TRL of 7 technology readiness level. In fact, we built up the first prototype in Buccino, the first pilot plant in Buccino near Salerno in Italy, that is made of 80 tons of sand and is charged by 1.9 megawatt of electrical power and can store up to 8.5 megawatt hour of thermal storage. The amount of energy is depending to the amount of the 10 tons of sand that is contained in a single module. In fact, we can build a different size of module. This one is the smallest one of the smallest size of the system, but we can build up a module that can reach storage of thermal energy between 10 up to 100 megawatt hour. But the main feature is that we can build a system made of different modules coupled together to reach up gigawatt hour of thermal storage. Mainly, the MGTES is 100% ESG compliant. In fact, is used only silica, sand, and steel as raw materials, but don't use dangerous materials or processes. All the technology used in this process are well known in the industrial sector. And we can size for different application. We can size correctly the power input and the power output to fit this system to integrate the system in existing energy system that can already exist. In particular, for example, to decouple the production of thermal energy and electrical energy for combined heat and power system. And finally, the MGTES can be used mainly to decarbonize and electrification of the industrial sector, but also, as we can see now, it's possible to provide flexibility services. Yes, because thanks to a due diligence that we already done with the Italian TSO Terna, and thanks to the electrical resistor that have a large quantity of power installed for each module, it's possible to modulate this power according to in order to provide different services. These services is referring mainly for the regulation of active power, then the regulation of frequency in order, for example, for the primary, secondary, and tertiary regulation. And it depends on the state of operation of each element. In particular, we can find for example, in charging and discharging phase, the fluidization, and both of those, the fluidization is already active. Then we can modulate the power in a quickest way compared to the case in which the MG test is in hot standby, when the system is ready to exchange energy, but the fluidization is stopped. In this case, before to provide flexibility services and to regulate the power, we have to activate the fluidization. And this, the startup of the fluidization requires less than 2 minutes. Then we can provide flexibility services in terms of regulation of the active power drawn by the grid in all cases, excepted the cold standby, in which the module is not in operation. Then, in conclusion, MGTES is a simple thermal energy storage solution that can be defined 2.0, because the thermal energy storage until now is figured as a simple container of water that can be heated up and then can reach reach other thermal fluid from processes. But in this case, as you can see in this picture, we can find a different application for MGTES as a long duration energy storage. But as all the energy storage system, MGTES cannot provide all the flexibility services alone. It's important to couple this technology with other technologies, in particular long duration energy storage. And mainly, the MGTES can, to summarize, can decarbonize the industrial plant, for example, to displace the fossil fuel usage, for example, to produce steam at different temperature level, increasing the penetration of the renewable sources, reducing also the curtailment of the production of this system, and also, as I mentioned before, can increase the flexibility of thermoelectric power plant, for example, to decouple the production of thermal energy and electrical energy. And also, last but not least, is useful for the recovery of power block of the thermoelectric power plant that are in the commissioning phase. Yes, because the steam produced by the MGTES can fit with a certain level of temperature and pressure, can fit and can recover this power block for the power-to-power generation. As you can see on the right side of this picture, the round trip efficiency is lower respect to the case of power to heat. This due by the inefficiency of the steam turbine that is lower than 40%. Then, in conclusion, is critical, as mentioned before by the Professoressa Maria Carmen Falvo, is critical to build up an energy storage hub composed by different technology of energy storage, in particular thermal, electrochemical, mechanical, and whatever, to meet the critical issues that the transition from fossil fuels to renewable sources are bringing. That's all. I think that I hope this presentation was good for you, is interesting. I remain available for any kind of information on the presentation and the technology. And
So